This is the second module in this three-part series on sleep neurophysiological dynamics through the lens of multi-taper spectral analysis. In the previous module, we discussed the drawbacks with sleep staging as a means of characterizing the sleep EEG. We then introduced spectral estimation as an improved means of analyzing the sleep EEG as it preserves more information than the traditional hypnogram. If you recall, spectral estimation is a powerful tool for analyzing oscillations. Methods of spectral estimation quantitatively break down oscillations in terms of all the different frequency waves that make it up and their oscillatory power. For dynamic or non-stationary signals, we generate a spectrogram that shows the frequency and oscillation characteristics over the course of time. This can allow us to isolate desired components of our signal from the confounding factors. Different methods of spectral estimation can produce drastically different looking spectrograms, but how do people actually compute these spectral estimates? In this module, we will answer this question, and by the end of the module, you will 1. Understand several common methods of spectral estimation, and 2. Be able to determine the parameters for multi-taper spectral estimation. Let's begin by discussing the simplest and most common method used for performing spectral estimation on EEG data. This method is called the periodogram. However, the periodogram is well known to be a poor spectral estimator. The most common way to perform spectral estimation is using a mathematical approach called Fourier analysis. Fourier analysis can be used to convert a time domain waveform into its frequency domain components by performing what's called the Fourier transform. You may often hear the term fast Fourier transform, or FFT, which is a specific implementation of this method, which works efficiently on computers. In theory, Fourier analysis assumes that any dataset can be broken up into a series of pure sinusoids of infinite length. Let's say this 10 Hz sinusoid has infinite length, and we can use Fourier analysis to look at the power spectrum. Since it is a pure 10 Hz sinusoid, it will be a perfect vertical peak at 10 Hz. Unfortunately, in reality, we have finite data, and when we simply use the Fourier transform of the finite data to estimate the power spectrum, this is called a periodogram. Instead of a perfect vertical peak, we get one big rounded peak in the center called the main lobe, and then this ringing that spreads off to infinity on either side of it, creating side lobes. The reason this occurs is because we can think of finite data as infinite data multiplied by a rectangular window where the signal value is 0 at every time except where we actually observe the data. Therefore, when we are computing this Fourier analysis that assumes the data is infinite in length, what happens is it ends up combining the power spectrum for the infinite sinusoid and the rectangular window. Due to the sharp changes in the rectangular window at the start and end of the data, the result we get is this wavy trace with one main lobe and infinite little side lobes. Since we live in the real world with finite data, we cannot obtain the perfect spectrum with one peak that we want. What this means is that the estimator has bias, meaning it will always differ from the ideal or expected spectrum. It is especially bad when the data length is short. There are two types of bias that we get. First is narrowband bias and is caused by the main lobe. The ideal spectrum is a perfectly vertical line, but with the periodogram, the main lobe has bandwidth. The implications of the main lobe's bandwidth are any frequency peak with a bandwidth smaller than this will be expanded to have this greater width. And if multiple frequency peaks occur within this bandwidth, they will be combined and only appear as a single peak. This determines the frequency resolution, which is the minimum peak width observable in our spectrum. The second type of bias is broadband bias and is caused by the side lobes. The side lobes can be thought of to act like antennae transmitting the power that should be in the middle at the expected frequency to false frequencies along the sides. This is known technically as spectral leakage. We are taking this perfectly focused power spectrum and spreading it out infinitely with these side lobes. So, how do we improve bias? As mentioned, the ringing of the side lobes is the result of using this rectangular window. The reason being, this window has very sharp cutoff edges to it. So, one of the ways of fixing this is replacing this rectangular window with a window that has smooth edges starting at 0, gradually increasing to 1, before decreasing back to 0. This smooth transitioning function is called a taper. There are many taper functions you can use, and in this case, we are showing a common one called a Hanning window. If we multiply infinite data by a taper function, we get tapered data, and this changes the spectrum. This is the single taper spectrum. This approach greatly reduces the broadband bias by pushing down on these side lobes and concentrating the power more within the main lobe. This also serves to increase the difference in power between the main lobe and the closest side lobes, helping us to better distinguish the main lobe frequency. However, this isn't perfect. This is occurring at the cost of broadening the main lobe. We are decreasing the broadband bias, but at the same time, we are increasing the narrowband bias. There are ways of understanding how wide this main lobe will be, and if you understand your frequency resolution and choose it wisely, there are ways of controlling it. Bias is one problem and is basically saying that your estimate is not going to look like the true spectrum. Another problem is variance, which is the noise in the spectral estimate. The periodogram and single taper spectrum have high variance. They are also inconsistent estimators because no matter how much data you collect, you will not reduce the variance. Looking at a 10 Hz signal, the periodogram is very noisy and the side lobes have significant power. For the single taper spectrum, we can observe that the power of the side lobes has decreased, but it still has a lot of noise. What we want to do is simultaneously reduce bias and variance. Back in the early 80s, David Thompson developed a method to do just this called multi-taper spectral analysis. During a regular experiment where you have noisy data but want to extract the true signal, what we often do is perform multiple independent trials of the experiment and average the results. The idea is that by averaging over multiple trials that have the same signal, the noise will cancel itself out and we will be able to observe the true signal. The difficulty in the case of EEG analysis is that we cannot perform multiple trials. We only have one observation for the data we are computing the spectrum for. Therefore, wouldn't it be great if we could do this with only the one trial? We can essentially mimic the performance of multiple trials through the application of multiple tapers. Before, we were talking about using a single taper, but there are a variety of differently shaped taper functions available to us. Rather than using a single taper to compute the spectrogram, multi-taper analysis uses multiple tapers and averages their spectra. As we mentioned before, there are many different smooth functions that can be used as tapers. In this case, the tapers we choose come from a special class of functions called discrete prolate spheroidal sequences, or DPSS tapers. The DPSS tapers have two important properties that make them special. First, the shapes of these tapers were developed to remove false power from the side lobes and concentrate it in the main lobe where the true frequency is. This reduces the broadband bias caused by the side lobes. Secondly, the shapes are all orthogonal to one another, meaning if you use them as tapers, they produce estimated projections of the data that are completely uncorrelated. This property allows us to average them together to reduce variance. Multi-taper analysis allows us to essentially take one noisy observation and, using these DPSS tapers, extract multiple independent projections of the data. We then compute the single taper spectra of each projection and average them to create the multi-taper spectrum. The multi-taper spectrum has a strong reduction in the side lobes, a very clear main lobe, and much less variance than either the periodogram or single taper spectrum. To summarize, all it takes to estimate a multi-taper spectrum is 1. Generate a set of DPSS tapers, 2. Estimate a single taper spectrum for each piece of tapered data, and 3. Compute the mean single taper spectrum. Here is single taper spectrum data from 3 points in time during sleep. Notice the high variance. When we generate the single taper spectrogram from this data, the result is fairly noisy, and it is difficult to distinguish how frequency structures are changing over time. However, using multi-taper spectral estimation, now shown in red on the spectrum data, we see that while the overall shape remains the same, there is a huge reduction in variance. When used to generate the multi-taper spectrogram, we see a large improvement in the ability to distinguish the changing structure over time. There is a great deal of open source code freely available that will allow you to easily compute the multi-taper spectrum using languages such as MATLAB, R, C, and Python. In order to use this code, it is important to understand the parameters involved in estimating the multi-taper spectrum. These parameters are n, the size of the data window, meaning how many seconds of data do you want to assess at a time, delta f, the frequency resolution. This is the bandwidth of the main lobe, and as previously discussed, this is the minimum distance between frequency peaks you expect to resolve. Tw, the time half bandwidth product, and L, the number of DPSS tapers to use. How do we figure out what these parameters should be? First, in order to establish the window size and frequency resolution, you need to figure out your assumptions. The first assumption is in regards to stationarity. When we pick a window, we need to ask ourselves, how long does the data stay stationary, or how quickly is the data changing? If we believe the data is going to be moving and changing every second, then we don't want a window that is 10 seconds long. Conversely, if we think it's changing every 30 seconds and we set the window for 1 second, we may be generating things that aren't really there. We need to make an assumption of how fast the data is changing, and that is how we set our data window size. The second assumption is with regards to the frequency resolution. Given the data, what is the smallest distance between frequency peaks that we want to be able to resolve? Answering this question is how we set the desired width of our main lobe, which we call the frequency resolution. With n and delta f set, you can then calculate the time half bandwidth product. The time half bandwidth product is simply our window size multiplied by our frequency resolution divided by 2. With the time half bandwidth product calculated, the number of DPSS tapers can be calculated. You multiply the time half bandwidth product by 2 and round this value down to the closest integer. Then you subtract 1 to arrive at how many tapers you should use in the spectral estimate. Let's consider an example. Let us assume that our signal does not change faster than 30 seconds. So, this is what we set our window size as. We do not care to observe any frequencies closer together than 1 Hz, so we set our frequency resolution to 1 Hz. With these two values set, we can use them to calculate the time half bandwidth product using the equation shown. As such, our TW value is 15 Hz seconds. We plug this value into our number of DPSS tapers equation and calculate that we should use 29 tapers in our spectral estimation. Therefore, the simple procedure for selecting the multi-taper parameters is shown here. How do these multi-taper parameters change things? Here we have some examples that show the results of increasing our frequency resolution while keeping our data window size constant. Increasing the frequency resolution value increases the number of tapers we use. The larger the number of tapers we use, the more we reduce the variance of the spectral estimate. However, by increasing the frequency resolution, we are widening the bandwidth of the main lobe, which results in the characteristics of the spectrogram starting to blur together. As such, we need to select the parameters in a principled way based on what you expect to observe to balance between reduced variance and adequate frequency resolution. In summary, the multi-taper spectrogram is a way of improving on spectral estimation. We started out with a periodogram, which has high bias and variance, moved to a single taper spectrum, which has a reduction in bias but not variance, then moved to the multi-taper spectrum, which reduces both bias and variance. When calculating the multi-taper spectrum, you select the parameters. To determine these parameters, you need to understand how quickly your data is changing and the size of the separation between frequency peaks. The multi-taper spectrum over time can be used to generate the multi-taper spectrogram, which shows us the dynamics of our signal over the course of time. In the next module, we will discuss how we can use the multi-taper spectrogram to characterize EEG activity during sleep.